Perfect. Content. Everyone can see my screen. Good.
Yeah.
Perfect. Present. So welcome to like machine shop intro to milling, or the mill. This is by far our most used machine in the shop, and get ready for an adventure. It's by me, Anirudh, and Damien and Alex again, who's here in spirit. All right, Damien, start us off.
Okay, so the topics we're going to cover in this presentation are the process of taking a CAD and making it into a print and then going through the shop, preparing the material, preparing to the machining process, and then programming. So from CAD to shop. So from CAD to shop, first you need to create a part on CAD, integrate it with the rest of the robot and make sure it fits well and all dimensions are correct and all the holes and such are where they need to be. Then after that, they would create a print for the shop, which needs to be approved by the mentors and the students. And each print would have dimensions usually originate from central point, like this. So the 0, 0 would be at the top left, usually, maybe on the top right. So preparing the material. Okay, so overview for preparing the material. So we want the material to be around the right size to machine. We don't want it to be like 3 inches off. So we usually cut it with an extra 1/8 to 1/4 inches for tolerance when machining. We'll use tools like calipers, rulers, scribes, T-squares, and even markers for marking the material where we need to cut it. So for sizing the material, we'll start with a raw material, then mark the materials to cut. We'll use tools like scribe and measuring tape, dial caliper, or the double beam dial caliper, which it's in picture of in the top right. And then tolerances are usually 1/8 inch for bars and 1/4 for plates. And the bandsaw is the most common machine you'll be using to cut the parts the size. So preparing to machine.
Can I ask a question before we move forward?
Definitely.
Yeah. How often are those calibrated, and are students responsible for making sure that calibrations are intact?
So yeah, before you start measuring, you want to make sure it's calibrated with the surface. Usually just drop it down, make sure that it's saying 0 when it's level with the surface. If not, you can change it as needed. And then whenever you're done using it, you want to drop it back down again to level surface at 0 for the height one. And then caliper is the same thing.
So you can 0 it, but you're not talking about actual calibration where its true measurement might change. Is there any worry about that?
I don't believe that has been a
That has never come up as a worry for us.
Maybe it hasn't been an issue, but maybe it's something we should be aware of just to make sure.
Yeah, it may become an issue, but we haven't experienced any changes in size that would be too significant.
What are our often tolerances when we're fabbing a part?
It varies sometimes depending on the part, but usually it's around 0.005 inches. Smaller or bigger. It can be a bit more, a bit less, depending on what the part is.
You said 0.005, so yeah. 5 mils, you'd say? I think that's 5 mils.
Roughly, yeah.
Okay.
Yeah.
That's not too bad, but we should double check if there's a manufacturing calibration date or anything like that. Make sure. Just maybe not important for what we're doing here, but important for future fabrication knowledge.
Yeah, we can check that.
Definitely.
Okay. Yeah. So overview. So you need certain tools at your disposal during machining, and they're all contained in a toolbox near the mill. but you won't be using all of them at once for each part. And if a tool does break, you don't worry about it too much. Everyone in fabrication broke a tool at one point, if not more than that. And we can factor it into, we have room in the budget to buy more tools if needed to an extent. Okay, so one of the tools you'll use is a calculator, which is just for basic algebra calculations that you might need to do. And we usually do up to 3 decimal places for all of our parts. And it's always in inches. And then caliper is for accurate measurement of parts, usually around 12 inches for the 12-inch calipers. And then it's also for ensuring that the program's in the right location. So if you program says it's 1 inch from the 0, you want to check with a caliper if that's true. And then you can also use the sharp jaws of the caliper for scribing. The other measurement tools are the vernier caliper, which is the bottom right. And it's like a dial caliper, but doesn't have a dial. It has more tick marks and such. And the measurement usually be lined up with the 0 on the caliper. And then the machinist ruler is a very accurate ruler that goes up to 1/64. And you probably need a magnifying glass to see it, which we usually have in a tiny bag in the with the rest of the tools. Okay, so vices and clamps. So the vise is usually used on the mill for holding the parts tight in place so they don't fall out while milling, since that can be very dangerous. And the clamp is used to hold multiple parts together or parts to a base plate and when we're milling plates. The most common clamp is canter twist clamp. You can see on the bottom right. Yeah. Then parallels. Parallels are used to elevate the part from the vise. And this is important since when you're drilling into the part, if you want to make sure that if you drill a bit lower than the part, you don't drill into the vise. So that's why we usually elevate it. And there's different thicknesses of parallels, like from 1/32 to 1/8. Drill bits used for drilling into material. And this can be done for screws or for tapping the hole so that you can put screws in there, or just a general hole to like put something into. And the operation speed for drilling is from 1,200 to 1,400 RPM, in that range. End mills are used mainly to cut materials. There are multiple sizes of them, but we usually use the 1/2 end mill. And there's different numbers of flutes for different operations. And the operation speed for end mills is from 2,400 RPM. The applications are cutting metal to size, creating circle profiles and such, or cheesing the part, creating a bunch of holes in it, basically. And then collets are used to hold our tools. So drill bits, end mills, chucks. And then chucks are used for certain tools that don't fit into the collets, and they're also nice for quickly changing tools if you're using a lot of different drill bits and such. And you usually put the chuck into a collet and then insert the collet into the spindle. It's very important to not use end mills with the chucks, as the chucks aren't really designed for the sideways motion of an end mill. And then stops are used for setting a common edge to base a program off of, so you can have a flat surface that you can depend on for zeroing off of. And there are different types of stops. There's a jaw stop, which is used for smaller parts, around 8 inches, and there's a picture of it at the top right. And then there's mill stop, which is for longer parts, like around 40 inches, and there's a picture of it at the bottom right. And the air compressor This is used to compress air through a motor, and we use to compress air around the shop to clean up our workstation to get rid of debris between parts. Then coolant and lubricant is used to keep the parts and tools from heating up too much. And we use an air compressor to spray the coolant out the part. And this is important since it prevents material from melting around the tool. And if that happens where it melts around the tool, it will harden and then break the end mill, which is not good.
So next is machining process. So this is from like sort of your start to finish of how you would utilize the mill. So first is like an overview. Each machine has a different purpose. The basic idea of milling is removing material to create a part. So like excavation, you have to be careful when removing material because you cannot undo it. So you just have to like take lots of precautions, measure twice, cut once. And limitations of the mill, only XY programmable, Z is actually manual, and operations are usually simple. Cheesing is difficult and requires another type of file. It's called a DXF file. And majority of the time, since now that we have a CNC, cheesing will be done on that and will never be done on the mill again because it is a very painful process. So first thing is cutting material to size. So it's measured to see how much you need to cut. Usually when you're using multiple, when you have to make multiple of the same part, when you're cutting with the bandsaw and you measure, you're gonna, and it's gonna be above like the needed amount. Usually choose the one that's closest to the needed amount, so i.e. the shortest, and you start off with that. And then you set your stop. Your stop is basically like used as a reference point so that you can line up your material each and every single time at the same position. So face off one side and first. So what that basically means is flatten out one side. You use end mill, slowly approach the side of the part and lightly graze it. The grazing it will simply flatten it, and then you can just flip it over and then do the other side. Set X as 0 and cut until the side is smooth. So getting that smooth side will help us when measuring it and making sure it's actually within tolerance. So face off other side, same process, make sure it's smooth, and then you set your X as 0 and machine only one of the parts. This is so that you can first measure, you can measure it down and see, okay, did I cut too much or too little? And if I cut perfectly amount, that's how much I cut for the next one. So measure to check how much more is needed to be cut, displace the cutter to the amount, and then cut to size, measure again, ensure the part is to the length, and then cut the rest of the blocks that you have. So use the smallest part as the first one, fully cut to size. It ensures the rest will be size and limits the potential for messing up every part. Messing up, this is just so like we don't mess up. Trust me, it has happened before, and it's painful to restart, knowing that all that you cut was not to size. So the next thing that you do is zeroing. So it's just find a flat surface to zero off. Either use the vice jaws, your jaw stop, your mill stop, or the part itself. Insert the edge finder tool and the collet into the spindle. So if you look at the diagram over here, this is your spindle, and then this is your edge finder, and then obviously inside there is your collet. And then turn on the mill and set the spindle to roughly 1000 RPM. We want to go a little slower with this one because the thing with edge finding is you're going to use your finger. And if it's too fast, you can actually hurt your finger. And one key thing to note is only change the spindle speed when the mill is actually on. If you do it when it's off, you're going to hear like a grrr sound, which is a bad sound, and we'll get mad. So then lightly hit the bottom part of the edge of the edge finder so that it starts spinning. Use your finger for this. It's completely safe to do it with an edge finder. There's no sharp edges on it. It's only at 1000 RPM. And then use the handles to your right and right in front of you to move the edge finder towards the surface of the part. And you want to do this process very slowly because the edge finder, it actually has a spring inside. So if you do it too fast, you can just snap it, and then that would be a broken edge finder right there. So this is also under zeroing. Continue until the bottom part of the edge finder stops spinning and deflects to one side. So what that means is when we hit it with our finger, it's going to start vigorously spinning. Once we get it closer and closer to the actual part and to the point where it touches it, it's going to stop spinning. And then you want to do it so that there's like sort of this breakage that comes in between. And that's when you know you've hit like your actual zero. And you want to do that like multiple times in order to be like perfectly accurate. And when you set that as your zero, and then you move 0.1 inches away from the surface. This is so that you can get it to the corner that you desire. Or in this image's case, it's going to be down here. So then set zero and repeat for X or Y. Usually you start off with your X and then just go to your Y. Next is base plates. So this is a very laborious process in setting up to use a base plate because this requires you to flip your jaws so that there is more support. So normally you see if you can see this side would be facing the plate, and then this edge over here would be facing towards you. But when using base plates for extra support reasons, because this base plate is very thick and like the regular side can't hold it, you have to flip it. You have to flip the jaw. So then that's how you use this. So then you just lay the base plate on the vise, map out locations of potential anchor points, ensure that there is no other hole around. So if you look at like this area over here, there's not that many, there's no hole around, and these are actually good points for anchoring down. What anchoring down means is basically securing the part by tapping into that, by drilling a hole, tapping into that certain point. What tapping means is putting grooves into that hole so that when you put a screw in it, it should go in and go out with ease. And then what we do from there is we put our plate, we clamp it down to the actual base plate, put our hole in, and then put a screw in there, and then put that at multiple locations where the holes actually need to be for the final part, and then take the clamps off. And then if you got your screws secured, the part theoretically should not be able to move anymore. And then you can work on your profiling from there. So next is programming. So the overview of the program, it's only for X and Y, it can be programmed. Like I said, Z is manual. And then ABS, that's absolute set from the absolute predetermined zero. So basically think of that as like your 0, 0. So this one of the features that we have is position drill. So it's an XY coordinate and automatically takes in from where you set your 0. So if I were to do like X end is 1, like the image says, and Y end is 1.5, you're going to go 1 inch to the right, 1.5 inches up. That's how it would do. So tool number doesn't matter too much, can be set in the tool table. Tool number is just a way for you to indicate like, oh, switch your drill bit, because some parts require different size of holes. So the tools that you would use here are drill bits, end mills, etc. And the speed that you would most likely want to go on this is again to that 1200 to 1400 RPM. It doesn't need to be that fast. So next is mill. So you start at your XY start position, and then you end XY, which is your end position. So your start position, which is your X begin right here. And then you have your X end and Y end right over here. So Conrad, how much the path should be curved at the end when it moves to the next continued mill. So basically, it's basically like the radius that it's supposed to form, and that'll be given by the part and through the CAD. Tool offset, left or right, always use left. That's just like a staple that we have in the machine shop to always go left. Next is the feed rate. So the feed rate is in the units for it is inches per minute, and it's usually around 14. Sorry. And then tool number must be set to the right diameter on the tool table. But you can access the tool table through the mill as well. And then you hit continue. You hit continue in order to go to like and select another mill or a position drill. So tools for end mill, for the mill, you'd always use end mill. And this is really fast, around 2000 to 2400 RPM. So don't be sticking your finger in there or else it'll chop it up. Next is the circle profile. If you see this, it's actually circle pocket, but there's actually no difference between the two. Circle profile just goes from the outside of the, like sort of from like the exterior to the interior, while pocket is interior to exterior. But there's honestly no difference in when we do it. So the XY coordinate, it's the center of the circle. So then the radius is the desired radius of the profile, which is also given by the CAD. And then direction always counterclockwise when inside. This is so that if we go counterclockwise, we're pushing the metal out, while if we go clockwise, we're actually pushing the metal in, which can get in the way when we're using the end mill. So the finish cut, it's always 0.005 inches. This is just for like the end to cut in order to smooth it out. So the feed rate in this case would be 10 inches per minute, or less for smaller holes. It honestly depends on the hole size for that one. So the finish feed rate, you want it always lower. So you get a nice finish and you get that smooth exterior that you want. Tool number, same as mill, must be set to the right diameter in the tool table. And then obviously use an end mill for this. Different sizes of the end mill, you can use a 0.5 or a 0.25 or a 0.125. And then for the speed, it's 2000 to 2400 RPM. Again, don't be sticking your finger in there. Next is the touch-ups, which is basically when you finished your product and you're just measuring it for the last time and just doing some cleanups. So measuring should happen while you machine. So periodically measure as you go in order to get some good, in order to like get the part that you want. So ensure parts are to size, ensure all elements are in the right place. You don't want a hole in a place where it shouldn't be, because that can really mess up the people assembling the robot, and it's not a good experience. Next is deburring, very important. You want smooth finishes. It's safety hazard, can cut hands. So when you're actually finished, like in one case profiling, you get, though it's smooth, the interior is only smooth, but then if you go to like the edges, it's very, very sharp. So if you actually just graze your finger over it, you gotta cut your fingers cut open. Simple as that. So what you want to do is take your deburr tool, or like the whirligig, like I talked about in a previous presentation, and you just want to clean that up. It should be to the point where if you take like that hole and you put your finger around it, it should be smooth. And then usually excess material at the end must be removed for safety and pass safety inspection. After every single part that we do, we always have a safety inspection run it. What that basically is you, the machinist, will run through it, and then another person or another machinist will take a look at it as well and see if you did everything right. So there's some tools that you would use, obviously the files. You would use the whirligig or the deburr tool, and then use a countersink tool. Countersink tools, again, are for holes. Files are for edges like this, and whirligig is for like the interior of it. So as you can see, this is a crown burr and this is a transient burr. Crown burrs are just like fully up and there's only on like one end, and it's like much smaller on the other. Transient is just like all are like roughly the same height. And then obviously this is a before after image of before deburring to after deburring. Next is Scotch-Briting. So it's similar to like sanding, but it's significantly less rough. So it's used to smooth out the surface of the part. We do something called anodizing, which is basically coating the metal in this sort of like black color. So and then in order to for that to be done, the part needs to be very smooth, because coming out of the mill, it's going to be very rough, considering like scraps flew all over the place and could have landed on the part, causing it to scratch itself. So you need to smooth it out, and must go with the grain of the metal. So you look at the direction at which like the metal is sort of like pointing. It's sort of similar to painting. You start one way and you end the same way. You don't start horizontal and go vertical. Same principle over here. And the main thing is making the part look nice, and usually given as a job to those outside of the shop. So if people find themselves like, I don't have any work, what can I do? We're like, Scotch-Brite. Next is cleaning. So make sure to clean up the mill, or else everyone will get mad at you. So clean up after you're done with work so that another person can work on the machine. You spray with your air compressor from top to bottom, and then use WD-40 on places where you use the lube and coolant. Anyone have any questions? I know it was a very much of an information dump because the mill is a very big process in order how to learn it. Damien and I both took 2 years to fully learn it. Same with Alex. So yes, trust me, the lathe and CNC are much more simpler than this.
Yeah. It's one of our more complex machines.
You promised 100 slides. Where are the other 75?
I said 40.
Oh, I'm sorry. I thought you said 100.
Yes, if it was 100,
You just made
we'd
it
be here
sound like
until
it was a lot of
It
work.
would have taken a long time. Oh, man.
What did you guys like take away from it? Let's start off with Joanna.
Honestly, it all kind of just, none of it like actually settled in. I just remember the deburring part. I'm still thinking about that.
Deburring, okay, what type of deburring? Like using the whirligig, using a file,
Yeah,
or
using
using a
the
countersink?
whirligig. Using the whirligig to file the hole.
Right.
Yeah, I don't know. And
Okay.
I also remember like the counterclockwise and the clockwise thing, and then one makes the metal go in, but the other one makes the metal go out.
Okay. So that's what's used. That's the direction of the end mill spinning.
Uh-huh.
So when you're cutting, you don't want to go clockwise because clockwise are going obviously to the right. And then when you're cutting, that means you're just like galloping over the metal like this. So what you're doing is you're actually creating your own barrier when cutting.
So that's bad.
That's a very bad thing.
Yeah, it's not good.
But what you're doing with counterclockwise is you're basically, for example, if I were to go clockwise, I go from here to here and then here to here. So I'm just picking up this residual off of the metal. But when I'm doing counterclockwise, you go the opposite direction, so you're just shooting it out as you're cutting it.
Oh. Oh, okay, that makes more sense.
Yeah.
Yeah.
That's a good one. I saw someone else start talking. Yes. Anyone else? Takeaways? You don't have any?
No, it's a lot. Like, obviously, I don't think I'll fully understand everything until I actually like get my hands on it. But yeah, that was very informational.
Definitely the thing. Yeah. Obviously, with our circumstances, we would not even have a presentation. Other sub teams might, but we would actually be in there asking you take pen and paper out, take some notes while we talk about each and every feature of the mill. If we get a chance to open the doors to the machine shop, all of you will definitely be invited to come in, and we'll show you how each and every single machine works. What about you, Katrin?
How many parts do we do like per season? Like, do we do a lot?
A lot of them. Quite a
A
lot.
lot is an understatement.
I don't know
Okay.
the exact number.
The exact number for each machine can range about 50, which is a lot.
Wow.
But like, yeah, so there's going to be a lot of work for the machine shop. It's a lot of hands-on work. And especially 1 week, it could be, it's our schedules like usually fluctuate. 1 week, it's all right. You only have to do like maybe five parts in the entire week. The other week, you have to do 10 or 15.
Yeah, it's really dependent on how many prints we get from the CAD team.
Right.
Hi, Mr. Deep.
Hi, Mr. Deep. How are you? You're muted, Mr. Deep.
He doesn't want to interrupt. He's just listening.
Yep. Hi, guy. You guys awesome.
Yeah, so there's never really a consistent number of parts that you have to do from one season to the next, because it really depends on the needs of the engineers and the needs of the robot changing based on different tactics, right?
Yeah.
Like for this upcoming season, our machining will be fairly low compared to previous, obviously, because we already have our robot. We just need to make improvements upon it. But in like a general season, you would be ranging about 50. Rough estimate. Anything else, guys?
Nice work. Good presentation, you guys.
Thank you.
Nice.
And this recording will be available to you guys. I'll actually see if I can email it to you, because this is a very hefty topic. So you might want to go over the recording again. I'll also send a presentation, go over the presentation again, so you can familiarize yourself with this.
Are we ready for me to end the recording?
If no further questions, I believe so.
So it's real easy to download the recording. You just you'll see it posted on our page when I end it, and you can download it for the next 30 days or so.
Yes, 30 days.
Yeah.
Just when you hit download, it doesn't auto let you save as, so you have to go into your download folder and move it to the folder that you want to.
Right.